Well, hello everyone, this is Mrs. Hansen, and in this instructional video we will be discussing a next reagent to prepare alcohols via a Grignard reagent. So we're introducing a Grignard reagent, and yet the overall process was going to be very familiar from the last video where we discussed reducing agents such as lithium aluminum hydride or boron tetrahydride. But this reducing agent has a key difference in how it works, but it also has an opportunity to introduce a carbon chain, an alkyl group, into its mechanism. So let's take a look. When I hear Grignard reagent, I want you to think about magnesium, a reducing agent with a general formula of RMgX. This is named after the French chemist Victor Grignard, who actually won his Nobel Prize in 1912, just in honor of his work with preparation of alcohols. What his work focused on was to take this bond, this carbon to bromine bond, and this could really be any R group, this just happens to be a benzene ring, but in any R group, he introduces a magnesium to separate the carbon chain, or this in case the benzene ring, and place between that this ionic salt of magnesium bromide. For example, here we have propyl chloride. When treated with elemental magnesium, we introduce the magnesium between the carbon and the chlorine, and what we've done is really characterize this bond going from a covalent bond to a pure ionic bond. Here we have a covalent bond between the carbon and the chlorine, and now all of a sudden we see this introducing a metallic ion, which we know to create an ionic bond. So this has a great deal of effect on the way the carbon is able to act as a nucleophile in this mechanism of turning a ketone or an aldehyde into an alcohol. So because we have this CMG bond, carbon is so much more electronegative than the magnesium. It's no longer considered a covalent bond, but it's considered an ionic bond. And we can see that this carbon that's attached to the magnesium is so much more electronegative that it actually creates a separation where we have electrostatic attraction holding them together, but not a shared pair of electrons. So that's the quality of an ionic bond, is opposite charges, which is a very strong type of bond, but they're not shared pairs anymore. And notice this carbon now with a negative charge. We're used to hearing it called a carb-anion. It is now has the ability to act as a nucleophile through a nucleophilic attack. And that's exactly what the mechanism has us looking at. Very similar to the last section where we had a lithium aluminum hydride, or just that extra hydride ion on a boron or aluminum to deliver a hydrogen. This allows us to deliver an R group and actually add some more carbon chain to the ketone or aldehyde and the formation of an alcohol ultimately. So a moment ago when we looked at the aluminum hydride or the boron hydride, it was the hydrogen that was coming up to attack the carbonyl carbon. That hydride anion added an H to go from sp2 to sp3. But with a Grignard reagent, we have a carb anion, and that is produced from the introduction of magnesium, creating an ionic bond. The carb anion then attacks the carbon in this position. This is the carbonyl carbon. Remember, this is a very strong electron withdrawing group, so this carbon is considered electrophilic. The positive charge is the attack site from the carb anion. We have changed that carbonyl from sp2 to sp3, but notice the key difference. Instead of just adding a hydrogen, we've actually added another R group to that chain that originally had the ketone on. And again, in the next step, we need to involve the solvent, where the solvent is then used to protonate the alcohol. And here now we've converted into a tertiary alcohol. So with the carbonyl carbon and the use of a Grignard reagent, we can attach yet another carbon. Mechanism resembles the reduction via lithium aluminum hydride or sodium borohydride, but the key difference is that we start introducing another R group to the starting material. So if I were to choose a boron hydride, negative charge there on the boron due to formal charge, or an aluminum hydride, negative charge on the aluminum due to formal charge there, we add a hydrogen on. But if I use a Grignard reagent, and a Grignard reagent is recognized as having that magnesium separating the methyl group and the bromide. And that means that I can treat this as an ionic bond, and the nucleophile here is a methyl group. So here is our carbonyl carbon. Here we would have a methyl, which would have C3H's, and then notice that it would have these negative charged electrons, and it would act then as a nucleophile. This bond collapses, and in the mechanism we would end up with a carbon now attached with a new methyl group and the negative ion of the oxide. And then of course the job of the solvent is to end up protonating the alcohol. So we've turned the ketone into a methyl hydroxide functional group. Notice also that you see on the arrow two separate steps. Step 1 using the Grignard reagent, and step 2 using the protonated solvent. Remember that with the boron tetrahydride, you could list those on the same arrow, but with aluminum and with the Grignard reagent, we must number the steps. Here we have a carbonyl carbon, and therefore it's the site of attack by the nucleophile. This nucleophile is CH3 negative because this now is treated as an ionic bond. And here we have the site then of the carbon anion having a nucleophilic attack on that electrophile, the carbon that's in the aldehyde here, the electron withdrawing group, making that partially positive. And at the end, because the Grignard reagent contained a methyl group, we've added on a new methyl group. And remember, this particular, because this is sp2 ending up to be sp3, we created a new chiral center. So remember that we'd have a racemic mixture. Both enantiomers would form. There's a parallel with esters as well to the hydride reduction mechanism from before. This is an ester. Remember the functional group, a carbonyl carbon leading out to another oxygen with an R group. So just remember that general structure of an ester. The ester has a carbonyl carbon and attached to another oxygen leading out to an alkyl group. Again, this particular reagent here has just a methyl group, but it doesn't have to be. It can be any number of carbons associated with that Grignard reagent. But because an ester has actually two attachments to oxygen, notice that we have an excess amount. You actually add this methyl group twice. So because there's two oxygens, you're going to see this mechanism very similar to the the double mechanism from a lithium aluminum hydride where we added two hydrogens. This time we're going to add two methyl groups and end up with a tertiary alcohol. So let me review last section and compare it to this new section just to kind of bring that mechanism back to your mind. Here we have an aluminum. Notice this here, the aluminum tetrahydride. So our formula here still puts the aluminum at a negative formal charge. And this hydride ion is really the source of the nucleophilic attack. So you see this hydrogen adding on to that carbonyl carbon, and then this bond collapses, and we formed this alkoxide negative ion. In our next step, we actually reform the pi bond. So the oxygen negative electrons reform that pi bond. Notice here that what we had in this particular case, when it reforms the pi bond, it expels the OMe. So that leaving group has to leave. We have a new carbonyl form. So notice this now, the new carbonyl is just ready for a second nucleophilic attack. So by the time we're done, we've added across 2 hydrogens from aluminum tetrahydride. When we compare that to an ester in a Grignard reagent, it's the exact same process, but instead of adding a hydrogen, we're going to add an R group. So step 1, you attack the electrophilic carbon, causing the double bond to collapse, and we form the alk oxide anion. So the job of the Grignard reagent, beginning to initiate the collapse of the original pi bond in the ketone, or the ester, and forcing the alk oxide ion to form, which then recollapses the pi bond and expels the OMe, this portion of the ester. When it does so, forcing that leaving group to leave, you now reformed a carbonyl carbon for a second attack. That second attack with the Grignard reagent introduces a second functional group, and at the end you've created that tertiary alcohol. Remember, we just used the solvent to protonate that alkoxide ion, and a tertiary alcohol will form. So the benefit of a Grignard reagent is introducing more carbon into the alcohol from the original ketone. So let's put it together with a practice. Show how you could use a Grignard reagent to prepare the following. Well, my first step is just simply locate the carbon that contains the alcohol. And when I think about the original structure, this is our benzene ring, leading out to the carbon that has the alcohol, and knowing that this particular structure had to contain the ketone, so it's kind of a retrosynthesis. What can I build that tertiary alcohol from? I can build it from a ketone. And then I want to just take a look at what else is attached. I can see that attached to this is a methyl group. Attached to it is an ethyl group, and attached to it is this benzyl group, this phenyl group, if you name it according as a substituent group there. So really we have some choices. If I had started with, let's say, a 2-carbon chain, the ethyl group, I could use a Grignard reagent to introduce the third, this methyl group. So one pattern would be to use a methyl Grignard reagent, starting with these 2 functional groups. If I start with a benzene and with the ethyl, I could introduce the third substituent and create my product. There's choices. What if over here I used a Grignard reagent and had the original molecule already have the methyl and the ethyl? So if I started with a ketone that had 1 unit of the 2-carbon chain and 1 unit of the methyl group, I could use a Grignard reagent to introduce the third, which is the benzyl group. So that would also work. Remember, we have to actually number these. 1, 2 would be the water workup to protonate the alcohol. But I see a third option as well. What if we used a Grignard reagent that introduced the ethyl group? So what would that original molecule look like? And if I think all of that through, I could have the original molecule, that would be the ketone, leading up to this carbonyl, and I could lead that down to just a methyl group, and that would lead us to introduce the ethyl with the Grignard reagent. So because there's 3 different groups attached to the alcohol, there's 3 possible workups to get there. and one is not any better than the other because a Grignard reagent is very flexible in terms of what the magnesium can attach to. The carbon directly attached to the magnesium acts as the nucleophile. Because of this ionic bond quality, we can introduce this benzene ring directly onto the carbonyl carbon and go through that process of creating the alcohol. So really, to reflect upon how we could create this, we had 3 different answers. We identified the carbon with the hydroxyl group, knowing that it came from a ketone. The ketone has to be the starting material. And then we just worked to identify all the groups that were attached to that position. We need to start with 2 of the 3 components on that carbon and use the Grignard reagent to introduce the 3rd. And so just looking at what we drew in all the possible answers, if I started with a phenyl, which is this ring here, I could hook it to the ketone, the carbonyl carbon, and have the ethyl group as another component we're starting with, introduce the third carbon chain, which in this case, the missing piece would be the methyl. Or if I started with the methyl, I could introduce the ethyl. And if I started with methyl ethyl, I could introduce the 3rd piece with a phenyl group. All of these are lovely choices. There is not one better than the other. When I have a tertiary alcohol, which was what our target was, we wanted to make this tertiary alcohol, you have 3 different ways to get there. Starting with a ketone that has 2 of the 3 components, introduce the 3rd via the Grignard reagent. It's a very flexible reduction reagent. Let's try one more. This is just from your homework. Show me a practical way of creating this secondary alcohol. 1, 2, 3, 4, 5. This is 2-butaneol. How would we make that? Well, again, there's choices. Because this is a secondary alcohol, you actually have 2 different pathways via Grignard reagent. And one is just as lovely as the other. So first of all, we need to identify what groups are hanging off in terms of the R group. What groups are hanging off of that carbon? I see that on one side we have a methyl, and on the other side we have a propyl. And this in the original molecule was a ketone. So let's begin with the first substituent hanging on it, right? Let's just put the methyl group on. And so this would look like this is actually now an aldehyde. And on the arrow, I could introduce the second R group, the propyl group, by making it the Grignard reagent. In the first step, we would add 3 carbons to the carbonyl. And in the second step, we would protonate the alk oxide ion. And the resulting the resulting structure would be an alcohol, and just remember that it would have an enantiomer as well. That's one choice. But however, what if we started with a 1, 2, 3 carbon into the carbonyl, and this again is an aldehyde because it's just a secondary alcohol. We could introduce the second methyl group that's needed with a Grignard reagent. So with just 1 carbon attached to the MgBr, creating a Grignard reagent, the water solvent to protonate the alk oxide ion would create the same structure. We'd end up with a secondary alcohol plus its enantiomer. So by identifying 2 different substituents on the carbon that has the alcohol on it, a secondary carbon, therefore we had 2 different reagent pathways to introduce one or the other R group to create our secondary alcohol. Very flexible. And that's really it for the Grignard reagents. They're very easy to use. And I think I'd like to stop the video here, give you time to process the Grignard reagent questions in your homework, and come on back to section, we have one more video to go. I'm going to put section 9 and 10 together in the last set of videos.